Let us look at the key growth measurement parameters. And this is still under agronomy. Remember, agronomy is the science of growing and managing crops. Now, key growth measurement parameters is the method of calculating by how much the crops are growing. Let's go into them.
And the first one was CGR, which is the crop growth rate. And we say this is the dry mass per unit ground area per period of time, whatever period you choose. And I gave us an example of a garden. We have our garden and we divide it into plots. And we have plots A, B, C, D, E, F, right? And we say, let's assume each of these plots is 1 meter by 1 meter. That means the area of each plot is 1 meter squared. So we grow our maize in the whole garden. Same maize, same conditions, same everything. And in the first month, we come and we are now getting our CGR. We come and we cut all the plants, the maize we have grown in this area A. We come and we chop all of it. That is at 1 month, at month 1. We chop all of it and we take it to the lab. And at the lab, we go and oven dry it. We get all of it smudged. 1 meter squared area, we get all the plants, then we take it to the lab, we oven dry it. After oven drying it, we determine the dry mass. And let's say for calculation purposes, our dry mass comes out to be maybe something like 20 kilograms. After 1 month, 20 kilograms. So 20 kilograms, that means our CGR, crop growth rate, which is dry mass divided by per ground area per period. So someone help me fill in these figures. What is our dry mass of the example given? Yes. What is the dry mass?
20 kg.
Okay, 20 kgs. What is the ground area?
Let's go back. Ground area is 1 meter squared.
So 1 meter squared. Then the period?
Let me see. 1 month.
1 month. So what will be our CGR?
20 kgs per meter squared per month.
Right. Agaton and Patricia, are we together on this point? How we have got the CGR? Yes. Agaton and Patricia, are we together to this point? Hello, are we together? Agaton. Are we together to this CGR crop growth rate? How we have got it? Okay. assume we are together. Then let's now have a look at a LAI, which is the leaf area index. So still get before we go to leaf area index, let's first continue with this. So this is CGR at month 1. Now we go and calculate CGR at month 2. So let's say month 2, we do the same thing. We go to field B, cut all the plants here, take them to the oven and oven dry them, then we measure and we end up with 10 kgs. 30 kgs. And the area is still 1 meter squared and the period is 1 month. So at the end of it, our CGR2 shall be 30 kgs per meter squared per month. Now we want to see between month 1 and 2, how much did the plants grow? So we shall say the CGR shall be CGR2 minus CGR1, which gives us 30 minus 20, which is 10 kilograms per meter squared per month. This is the actual CGR over the period. I don't know if it makes sense. Between month 1 and month 2, that is the growth rate. So now with these figures, we can compare with different varieties, different conditions, and we see which one is more optimal. Now with that, let's move on to the leaf area index. So just to preface this, we know that plants growth is brought about by their, let's say, food, how they consume their food. And we know plants make their food from photosynthesis. And we know for plants to carry out photosynthesis, they require light. We also know that the light is trapped using the leaves. So therefore, by measuring the area of the leaves, we are somehow able to know the growth rate. I don't know if this makes sense. So what we do to find the leaf LAI, leaf area index, we get the total leaf area in a given area of ground divided by ground area. So if I were to use this, so if we had to use this illustration, we know the area is 1 meter squared of each field. So what we go and do, we have our plants in an area. Right now say leaf area index of area A. Okay, leaf area index, because of since it's a ratio, it is the same. If you calculate for area A and B, or the whole field, it is the same as long as the conditions are uniform for growing. So leaf area index, we shall go ahead and get the number of leaves times average. Let me write it maybe more clearly. Small leaf area index, number of leaves times average area of leaves. AL is average area of the leaf divided by the ground area as well. So let's use an example of the maize, and we know that on maize the leaves are slightly big. Maybe on average, each leaf is 20 centimeters squared. This is 20 over 10,000 meters squared, which is the same as 0.001234 002 meters squared. So we go in our area. In area A, in total they are, this is the average area of a leaf, which is the AN in this case. Then we know in area A, they are maybe 300 leaves. So our total leaf area shall be 0.002 times 300, which I think gives us 6 meters squared. So if this is correct, then our leaves, let's say there are 30 leaves. 300 is a big number, 30 leaves in a meter squared, 30 leaves. This gives us 0.6 meters squared. That means our leaf area index shall be 0.6 divided by 1, which gives us 0.6 meters squared of leaves per meter squared of ground. I don't know if this makes sense. Are we together? I would like to get your feedback. Are we together? Amina, Agaton, Patricia?
Yes, sir.
Yes?
Yeah, I'm following.
Okay. Amina, are we together?
I'm following, but
Patricia, are we together?
I'm lost.
Where?
And I'm not understanding. Like, I'm not. It is not visualizing in my brain how, because I asked the AI and they're like it's like a canopy thing, and I'm not seeing it how it reflects. To be honest, could you kindly break it down? Like, are you going to measure every area of the leaf, then divide by the ground on which each leaf stands? Over.
Okay, yeah, that's a good question. So we could, in theory, go and measure every area of the leaf and end up with the correct total leaf area. But then that is complicated, right? But then what we can do, we can sample one plant and go and measure its total leaf area. For one plant, we measure its total leaf area and we measure the area of each leaf for that one plant. Then after that, we divide by the number of leaves to get the average area of a leaf, right? Then using that average area of a leaf, we can now go to the area. Let's say we have picked an area of 1 meter squared. And in a uniform field, you know, when we are sampling, what we consider. And then for this area, we go ahead and count the number of leaves in this area and multiply by the average leaf area. Because if, let's say, let me try to illustrate this. This is your plant. From as seen from above, you find it's something like this, isn't it? Does this make sense? Patricia, I'm with you.
Like, I understand. So what you're trying to say is that the leaf area equals to like a sum of leaves together divided
Yes.
by the number of plants equal to one average.
Pardon, what have you said?
The sum of leaves together, like for example,
Number
I
of
have
leaves.
yeah.
Number.
Then the number of like you get the sum of leaves divided by the number of plants on which those leaves are, giving us the average. Is that what you're trying to say?
Like, okay, we first find the average area of a leaf for a given plant. We go to the garden. This is plant. Let's see, P, Q, R. And they are all in an area of 1 meter squared, right? It would be so hard to go and calculate the area of each individual leaf of every plant in this area. So what we do, we say plant P, we sample plant P, we go and we chop off all its leaves, we go and we go and measure the total area. So let's say the total area comes to maybe 0.02 meters squared. But then in total, it had 10 leaves. So therefore, the average area of a leaf is 0.002 meters squared. 10 leaves. You get it?
I get you.
Okay, now after we have got this average area of a leaf, which I'm calling AAL, now we can go back to the field. Sample our area of 1 meter by 1 meter, which is 1 square meter, and we count the number of leaves here, and we multiply by the average number of leaves.
Then you do what?
We count the number of leaves times this average area of a leaf.
So we find the middle part of every leaf.
Yes?
We find like a middle part of every. Okay, how should I say this? We find like an average of the leaves in the garden, and
Yeah?
then after I find the average of the leaves, we count the number of the leaves.
We find the average area of a leaf.
Okay.
Then we multiply by the number of leaves.
The number of leaves of each plant or the number of leaves of the plant.
The plant of all the plants P, Q, R, S in that area.
What if the plants are different, like intercropped?
Oh, that's what was bringing the confusion. So here we are looking at one crop. We want to understand what is the growth rate of maize alone. So growth rate, you look at plants as individual units. Or a specific plant, actually, when you look at maize, you're going to look at only one variety of maize in a given area, maybe in Teso, maybe in Kampala, and that's how it performs. I don't know, is it now clear?
Okay, you go on.
Yeah. So we go to plant P, we cut off all its leaves, we take them to the lab, we measure the total area of all the leaves, and we divide by the number of leaves. Average area of a leaf is total area of all leaves of plant P divided by the number of leaves on plant P. And here we add the total area comes to 0.02. We divided by the 10 leaves, which gave us 0.002 meters squared. Then we go back to the field, sample, maybe a different area. Now let's say we sample an area with plants, maybe L, M, N, O. And we count the total number of leaves here, which ends up maybe being 30, right? In this area. So 30 times the average area of a leaf. This is a calculation I was doing here. So area A had 30 leaves, right? We know that our average area of a leaf is 0.02 meters squared. So our total leaf area is 0.002 times 30, which gives us 0.6 meters squared. And our leaf area index, remember we said it is the total area of the leaf, total leaf area divided by ground area. But our ground area, we did 1 meter squared, isn't it? Right? So our answer will be 0.6 meters squared of leaves per meter squared of ground. Are we together on that? Yes. Amina, Agaton, Patricia, I would like your feedback. Are we together? Do you have any questions?
Hey, Aaron,
Yes, Agaton.
I got kind of confused somewhere. I don't know why.
Yes.
Mm.
Which part? Okay, let me ask. Were we together on a crop what? Crop growth rate.
Crop growth rate. Okay, we're together, but I didn't get it well or perfectly.
Let me go through it once again. So these things, these calculations, they are not done by ordinary farmers. They are done by researchers. So now
Okay.
a researcher, maybe NARO has released a new variety of maize. And the researchers at Carbon want to find out, really, this new variety, does it grow really faster than the normal ones?
Okay.
So what they do, they plant it in a field. Then they go and now sample. The field is now divided into areas of 1 meter squared, right?
Okay.
So crop growth rate is the dry mass per unit ground area for a given period. Dry mass. So you get all the plants in 1 meter squared. That is, our area is 1 meter squared. The period is after 1 month. So you go get the plants 1 meter squared, collect all of them, the leaves, the stems, everything above ground. Take them to the lab, go and put them in the oven, and you dry them until all the water is out, most of the water. Then you measure its weight. So at month 1, let's say you end up with 20 kgs, right? That means the CGR is 20 kgs per meter squared per month. Then at month 2, you end up with 30 kgs. So 30 kgs per meter squared per month. Now you want to see between month and 1 month to by how many kgs did this maize plant grow. So you subtract the CGR2, which was 30 kgs per meter squared from, then you remove 20 kgs per meter squared, which gives you 10 kgs per meter squared. That means between month 1 and 2, this plant grew by 10 kg per meter squared. Now you're able to compare and see that our plants previously have been growing by 9.5 kgs per meter squared. This new variety is growing by 10 kgs per meter squared. You see the difference is not significant. So then you make decisions. But if your old rate has been maybe 4 kgs per meter squared per month, and now it's at 10, then now you say, yeah, the new variety is significantly more productive than the old one. Faster growing, okay. Now, when we went to leaf area index, the premise behind all of this, the reason why we calculate leaf area index is because we know that for plants to grow, they require food, and plants make their food by photosynthesis. Plants require light to carry out photosynthesis, and the light is trapped using the leaves, right? So with that knowledge, the area of the leaf, you can conclude affects the growth rate. So what are you going to use to measure the leaf area index? You know that leaves, when the leaves are in a plant, first of all, they don't cover each other normally. Find that inside if it's like a mango tree, if you climb inside, you don't see leaves. The leaves are at the edges so that each of them have access to light. They are not obstructing each other. So you go ahead and get the total area of the leaf. You're here, what you're trying to measure. So it's mentioned earlier here. Let me show you. You're trying to measure the light interception potential. Remember, the leaf is responsible for intercepting light. So by using measuring leaf area index, you're measuring the light interception potential, which can give you an idea of the growth rate of the plant. So what you do, you go to an area, maybe of 1 meter squared, and you get the total leaf area. There are many ways to do it. I've demonstrated one, but you don't need to know it. In simple terms, you can go 1 meter squared, get all the plants, cut off their leaves, and go and measure, maybe by counting squares because they're irregular shape. Then you get a total area divided by the ground area. And with that, you're able to find your leaf area index. And now moving forward to the last one, which is the net assimilation rate, which is dry matter increase per unit leaf area. It measures the leaf efficiency, NAR, net assimilation rate. So net assimilation this is the NAR. It measures the dry matter increase per unit leaf area. Dry matter increase per unit leaf area. And in simple terms, NAR is equal to the CGR divided by the LAI, leaf area index. I won't go into the details for now. Time is against us. Let's move. Then I'll share the video. You can rewatch it as much as you need to understand. I'll also get videos from other sources and share them with you, so that this concept is clear before the next lecture. So these are your crop's vital signs. A high LAI means the crop canopy is capturing most sunlight, good for a dense bean field in Kabale. CGR tells you how fast the whole field is producing biomass. NAR tells you how efficiently each leaf is working. If NAR is low despite good LAI, maybe there is a nutrient deficiency in the biomass bean. Now, source and sink dynamics. Source plant parts that produce photoassimilants, e.g. mature leaf, then sink plant parts that use or store the assimilants. So we have source, mature leaf. Sink can be the root tubers, stem tubers, or the fruits. So we have a source, and it's basically the source and consumption, what they are talking about, source and sink, where what produces, then what consumes or stores. The concept is simple. The leaves, mature leaves produce the food, then the grains, the roots, the fruits, they store the food. Translocation is simply the movement of sugars from the source to the sinks. This is the supply chain within the plant. The source is the factory, which is the mature leaves, and the sink is the market or warehouse, which are the grains, fruits, root tubers, stem tubers, whatever. If a sink is weak, like poorly pollinated maize ears, the factory slows down. Managing for strong sinks, good pollination, and healthy sources, e.g. pest-free leaves, is key for cassava growth. The root sink strength ultimately determines the yield. Now, on this concept of source and sink, are we clear? The source are the leaves. The sink is wherever the food is stored in the plant. For root tubers, it's the roots. For stem tubers, it's the stems. For fruits, it's on the fruits. For grains, it's in the grains, like maize. They're stored in the grains. Agaton, Patricia, Amina, are we together? Can I hear from you people?
Yes, Aaron, I tried to get it.
Patricia?
Yeah, it's a fair thing.
Amina? Are we together? Amina, are we together? Yes? Okay, I want us to look at the quiz faster, then we can conclude for today. There are only 10 questions, so it shouldn't take us long. Amina, are we together? So Agaton will give us the answer to the first question. Define development in plants. Yes, Agaton?
Yes, Aaron.
Define development in plants.
I would say development in plants refers to the changes in size, function, and structure that occur within a plant.
Okay. The systematic progression through recognizable stages during a life cycle. So in the beginning, we saw the difference between growth and development. We say growth is basically increase in size, whereby we saw photosynthesis, cell division, the plant was increasing. Then growth, development, we say these are progression through stages. So it's from a seed to flowering to providing fruits and like that. So the first stage looked at before flowering, then from flowering to pollination, then after pollination. Those are the stages of development of plants. So development is the systematic progression through recognizable stages during the life cycle of a plant. Patricia, which growth phase is characterized by ear or panicle initiation and pollination? Yes, Patricia?
I'm not sure, but I think it's the mature stage.
So it's the reproductive or flowering and fertilization stage. We are the first stage, second. So this is the second stage. And the maturing stage is the third stage, whereby it is forming grains or fruits or whatever. What does LAI stand for and what does it measure? Amina, are we together? Yes. Okay, Agaton, help us with that one.
We are together. I'm on.
Okay. What does LAI stand for and what does it measure?
It is leaf. This one.
Area. Leaf area index, okay? What does it measure?
It measures the size of area per meters. Oh, it's out of my mind.
So LAI is the leaf area index, and the leaf area index measures the leaf area. LAI is leaf area index, and it measures the light interception potential of a plant. By how much of the light do the plants capture? Leaf area index is the ratio of leaf area to ground area, indicating the proportion of ground covered by leaves. Okay, this is, I think, for Agaton. In the source sink concept, what's the sink? Yes, Agaton?
A sink is a plant part where I'm forgetting.
Okay, what is source?
Source sink concept. Oh, Aaron, a pass.
So source is where the mature leaves, the ones which are responsible for producing food for the plant. Then sink is where the food is stored. In fruits, in the fruits. In maize, in the grains. In stem tubers like Irish, in root tubers, it's in the roots like cassava potatoes. A sink is a plant part where photoassimilates are utilized or stored. Can be roots, grains, or developing fruits. Photoassimilants, just take it as food, the product from photosynthesis. This goes to Patricia, I believe. Complete the sentence. Translocation is primarily the movement of sugars from dash to dash.
It's the movement of sugars from the source to the sink.
Perfect. Amina, why is the reproductive phase, market phase 2, considered critically sensitive to moisture stress?
Reproductive phase is
Yes.
where flowering occurs.
Yes. All right, that's right. Reproductive phase is where flowering occurs, and we know it involves pollination. So because this phase involves key processes like pollination and fertilization, which require adequate water and nutrient supply, water stress during this phase can lead to poor pollen viability, failed fertilization, and directly reduce the number of grains of fruit set. Okay, next is Agathon. Explain the practical difference between crop growth rate and the net assimilation rate.
Pardon?
Explain the practical difference between crop growth rate and the net assimilation rate.
Crop growth rate.
You can tell us simply what they measure.
What they measure?
Okay, if you can answer the question, it's okay. If you can't answer the question, you can just tell us what you know about them.
Okay, what I know about them. The
Yeah.
gross crop rate, the total production of biomass of the plant. Then,
Yes, for unit area.
then the net assimilation rate is the efficiency of the biomass production per leaf area.
All right. CGL measures the short time productivity of an entire crop stand per unit land area over time. It's useful for assessing field level performance, while the net assimilation rate measures the efficiency of individual leaves, indicating how effectively a unit of leaf area is producing a matter. This is useful for diagnosing leaf level health or stress. This goes to whose question is this, Patricia? A rice farmer in Butaleja notices his crop has a lush, dense canopy, which is a sign of high leaf area index. But the panicles produce a small and poorly filled. Using the source seek concept, what might be the problem? Wow.
Okay, I think
Yes.
there is production of photosynthesis, there is production of the photoassimilates, but they are not able to reach, they are not utilized. Okay, the source is active, but the sink is inactive. That's what I think.
Wow, that's very good. So yes, the food or photoassimilants are not able to fully be taken in. Maybe because at the pollination stage, they got the panicles were first maybe to have stress. That's what they're giving. This score is likely weak sink strength. The source leaves are producing assimilates, but the developing grain sinks are not able to attract or utilize them effectively. This may be due to poor pollination, genetic factors, or disease affecting the panicles. I believe this is for Amina. You are monitoring maize field in Captura. How would you determine if the crop has entered the grain filling stage phase 3 without laboratory tools?
Because phase 3 is the drying phase.
The grain filling phase, like fruiting phase, or grain filling, or tuber, something like that.
You can notice change of shape, not change of shape, change of color of the leaves.
Okay. All right, let's see. So you observe the plants. The key indicators include silks have dried and turned brown. Canals are visibly developed on the cob in the blister or milk stage, and no new leaves are emerging from the pole. Yeah, so this is the stage after pollination. So what do you observe after pollination? They are giving examples of silks have dried and turned brown. Canals are visibly developing on the cob. And this is for maize in the blister or milk stage, and no new leaves are emerging from the hole. This goes to Agathon. A report on a sunflower trial in Lira shows a high specific leaf area. What does this suggest about the plant's growth strategy and likely soil conditions? Wow.
Report.
Yes.
I'm trying to figure it out.
Yes.
What does this suggest about the plant's growth strategy?
Let's see the answer. These questions are becoming technical. A high SLA indicates green leaves with a large area per unit weight. This suggests a plant strategy optimized for rapid growth and high light capture in resource-rich conditions like good water and nutrient availability in the trial. It is a strategy for maximizing growth rather than conserving resources. All right. And I think with that, we have come to the end of today's session. I would like to thank you who have been actively participating and have managed to be here today. I will